All right, welcome. Have you ever seen a robot in action and just wondered, how on earth does it do that? From a giant arm in a factory to a tiny tool in a hospital, there's this surprisingly simple logic behind how they move. So today, we're going to pull back the curtain and figure it all out.
Really, it all boils down to this one big question, doesn't it? How do these machines pull off these incredibly complex and precise movements? It can seriously look like magic, whether it's building a car or exploring Mars. But here's the thing. It's not magic at all. It's just brilliant engineering. And we're about to break down exactly how it works.
So here's our game plan. We're going to start with the absolute basics, the fundamental building blocks. Then we'll get into the robot skeleton and the parts that actually make it move. After that, we'll see how all those pieces connect together into something called a kinematic chain. And finally, we'll talk about why this is also important.
First things first, the building blocks. The secret to understanding how a robot is built is realizing you already know the blueprint. Seriously, that's because it's basically modeled on us.
It honestly is this simple. A robot's links are just like its bones. They're the rigid parts that give it structure. And the joints, well, they're its joints. Like our elbows and knees that let us move. If you can just get this one core idea in your head, I promise, you're already halfway there to understanding how pretty much any robot moves. This is the key.
Okay, so let's zoom in on that first piece of the puzzle, the skeleton, or what engineers call links.
So at its core, a link is really just a rigid part. The easiest way to think about it is as the bone of the robot. Its main job is to provide strength and connect one moving part to the next. It's the stuff that holds everything together while the robot is doing its thing. But, their job is so much bigger than just being a solid piece of metal. Links actually define the robot's entire geometry, how far it can reach, how stable it is, and this creates a huge engineering challenge because they have to be incredibly strong, but also super lightweight. That's why you see them made out of things like specialized aluminum or even carbon fiber. And their shape, it totally depends on the robot's job. A big industrial robot will have these long, straight links to reach across a factory floor, but a humanoid robot will have links that are shaped just like our own arms and legs.
Now, a skeleton made of just links would be, well, pretty useless, right? It's just a statue. It couldn't move at all. And that's where our next section comes in, the joints. These are the real movers and shakers.
So a joint is simply the connection point that allows one link to move around relative to another one. This is what gives a robot all its mobility, what engineers call its degrees of freedom. And just like in our own bodies, there are a few different types, and each one is designed for a very specific kind of motion.
First up is the rotational joint. And the name pretty much gives it away, right? Its motion is circular, just like your shoulder or your elbow. This is the absolute workhorse joint you'll see in most of those big industrial robot arms, letting them pivot and swing tools around with amazing precision.
Okay, next we have the prismatic joint. Forget about rotating. This one is all about moving in a straight line. Think of it like a piston, just sliding back and forth. You'll find these all over the place in things like robotic grippers that need to open and close, or in mechanisms that have to lift something straight up and down.
And finally, we get to the spherical joint. This one is the most complex of the bunch because it allows for rotation in multiple directions at once. The perfect human example? Our ball and socket hip joint. These are absolutely essential for humanoid robots that are trying to copy the complex, fluid movements of a person, like walking or trying to keep their balance.
Okay, so we've got our bones, the links, and we've got our movers, the joints. Now let's put it all together. When you combine them, you create something that engineers call a kinematic chain.
I know, kinematic chain sounds super technical, but it's actually a really simple idea. It's just the sequence of links and joints, all connected in a row, starting from the robot's stationary base and going all the way out to its hand or its tool. This chain is what defines absolutely everything the robot can possibly do. It's the complete recipe for its movement.
And get this, building one is surprisingly simple. You just start with a rigid link, then you add a joint so it can move, and then you attach another link to that joint. Boom, just like that, you've created a basic robotic arm. Every single complex robot out there is built on this exact same idea, just with more links and more joints added to the chain.
So why is this so important to understand? Because the specific design of that kinematic chain, the length of the links, the types of joints, the exact order they're in, that is precisely what makes a robot good at its specific job. I mean, just look at the difference here. An industrial arm uses those long links and rotational joints to get the incredible reach and precision it needs to weld car parts. A humanoid robot, though, uses a kinematic chain that's designed to mimic our own skeleton, so it can do something as complicated as walking upstairs. And then you have medical robots, which use these tiny, miniaturized links and joints to perform unbelievably delicate surgery inside a person. The design is the function.
You know, one of our sources put it perfectly. It said that the careful design of links and joints is what transforms robots from static machines into dynamic, functional systems. That's really it. It's the essence of robotic motion. It's what brings them to life.
And that kind of brings us full circle, leaving us with one last really fascinating thought. We started this whole thing by comparing robot anatomy to our own. So as this technology keeps getting better and robots become more and more sophisticated, are we going to reach a point where their mechanical skeletons become almost indistinguishable from our biological ones? Definitely something to think about. Thanks for joining me.